everyone. My name is Katri Kakko and I work for EOS Finland. Today in this presentation, I will talk you through some of the key findings that we made in our TI64 ELI aging study. First, I'd like to acknowledge that this is not just my work, but also other colleagues from EOS Finland were involved and made this study possible. Secondly, I would like to get slightly acquainted before getting started. So, EOS Finland is the Metal Competence Center for inside EOS. And in addition to the production of our metal powders, we also have a very strong focus on R&D. And we are mainly responsible for the development of our metal materials and processes within EOS. Myself, I have worked for EOS for 6 years, and I'm mainly responsible for our titanium materials and processes. Now, let's get started with the topic for today. So, titanium aging. I will first talk you through some of the basic principles in titanium aging, and then show you some of the experimental methods that we used in this study. And then we will go through the major findings that we made on the powder and the parts. So, aging of powder. That is considered to be changes in the powder properties and chemistry within multiple process cycles. Why the powder ages is because, especially in laser powder bed fusion, when you melt your material with the laser, the molten material is in contact with the inert process atmosphere. So although the process atmosphere is inert gas, there's always some residual oxygen and nitrogen and hydrogen there that can react with the hot material. Now the titanium is especially reactive with oxygen. Rapid oxidation and pickup of nitrogen and hydrogen can happen in the melt pool. In addition, the hot spatters, which you also see in the picture, can react with these elements in the process chamber. These spatters come in various shapes and sizes, and they usually land on the powder bed. The larger spatters are removed with process sieving and therefore do not really contribute to powder aging. However, the smaller ones stay within the powder and can accumulate in multiple process cycles, therefore increasing the overall oxygen concentration of the powder. Now, obviously, we at EOS Finland love our powders and we want to study them. But why should you be interested in powder aging? It's because for a good quality product, you will need three things: a robust machine, process, and then high quality powder. Now, the machine and the process, they are sort of constant throughout the use cycles. But what if your powder changes? What does that actually do to the part quality? So this is something that we wanted to see. What's the scale of aging in our powders, and how many cycles can we use the powder, and what's then the impact to the part properties? Now, for the experimental method, we we wanted to do a study which would actually have some relevance, and we could see the aging effects throughout the study. We also wanted to reach high number of cycles, meaning that we needed a lot of powder. Uh, for us to do this with a lot of powder and still constantly age the powder, we needed to divide the powder into 3 sublots. Each of the sublots went through the same cycle for 5 times, meaning one cycle is the sampling of the powder, building of the parts in the machine, and then finally sieving of the powder. So we did that for each of the sublots for 5 times, after which we blended to get 2 sublots, and finally blended all of the material together and just used until we didn't have enough powder to run the test job anymore. This basically resulted in more than 600 hours of machine time and more than 500 hours of laser on time, so exposure. For this purpose, knowing that the exposure will actually age the powder, we selected a job layout where we would have our test specimens, so meaning bars and cubes for mechanical and chemistry testing, but also some application parts where we could have a range of different exposures, and this would hopefully bring our study closer to what's the real case in industry. For the study, we used our EOS M290 workhorse and Ti64 ELI powder with the 40 micron process. For the actual results, we measured the full chemistry both in powder and solid parts, but we only saw changes in the oxygen, nitrogen, and hydrogen contents. For all of these elements, we saw an increasing trend in the results. However, all of the results were still within standard requirements after 22 cycles. In these graphs, you can see that the black dots are the solid parts and the gray squares are the powder values. We can see that the solid parts are always higher in oxygen, nitrogen, and hydrogen concentration compared to that of the powder concentrations. This is due to the pickup of elements in the melt pool. Why I talk about trends here is because if we take, for example, the oxygen results, the start level and the end level of oxygen, the difference between these two values is actually still within the measurement uncertainty of the method that we use to measure these values, fusion, and therefore we cannot really say that there is a significant difference between the start and the end. However, there is a trend as would be expected from theory. If we look at the static mechanical values, we can see that there is a trend in or an increasing trend also in the strength of the material. The elongation is not as much affected. Here we did the testing at every 5th cycle, both in horizontal and vertical orientation for heat-treated properties. And again, we can see that there is a trend or an increasing trend in the strength, but everything is still well above the standard requirement limits. But what is interesting is that if we map the strength of the material and also the oxygen concentration of the powder in the same graph, we can see that both of these trends go quite well hand in hand. And this is a known effect in titanium from conventional manufacturing. And I think that it's a good thing that not everything in additive manufacturing is new, but some of the very basic principles also apply here. If we look at the powder properties, we can see that the particle size increases with increasing process cycles. And here on the right, we have the medium particle size as D50 value. And you can see that that also has an increasing trend, which is at least partly explained by the graph on the right-hand side, which gives the amount of fine particles, in this case, minus 15 micron particles, which has a decreasing trend. And this is explained by the fact that these small particles are very light and tend to get airborne during the different process steps, for example, during sieving, and therefore are easily removed during repeated process cycles. If we look at the SEM images, we can also see the same results here visually. So the cycles increase from left to right, and you can see that the amount of fine particles in the images decreases, but you can also see some larger particles increasing. And basically, if we take a look at the morphology of the powder, which is the shape and surface of the powder, we can see that there is no significant difference in that with the increasing cycles. We also measured that using dynamic image analysis, and we confirmed that there was no significant difference in powder morphology between cycle 0 and cycle 22. If we get this information and combine it to other aging studies, for example, our own aging study on EOS nickel alloy HX, we actually saw there that the powder morphology did change significantly over multiple process cycles. And for us, that indicates that aging phenomenon could be material, process, and even machine specific. We also used photodiode-based monitoring equipment in this study, so Eostate melt pool. We used that data to construct two images that I have here on this slide. So basically, we used the signal data to construct one of the density cubes at cycle 1 and at cycle 20. What we can see from the data is that the signal variation did not significantly increase with the increasing process cycles. And for us, this confirms the results that we also had from the tensile testing. Also, these results indicate for us that maybe in the future, um, monitoring devices could be used to monitor when your powder needs to be replaced. So when the quality goes bad. With that, I'd like to conclude that we only saw minor changes in the powder properties. Um, we did see an increasing trend in especially oxygen and nitrogen, and we could link that with the increasing strength of the material. However, despite these changes, we did see that all of the material standard requirements were still fulfilled after 22 cycles of use. And everything here to us indicates that basically aging can be material, process, and even machine specific. If you have any questions, I will take them live shortly. But do reach out to us, so you can reach out directly to me or my lovely colleague in North America, Laura Gilmore. And we also have a white paper available for these studies. With that, thank you for listening, and I will be now taking your questions for the presentation.